We are going to learn today how to maximize the volume of a box, and this is applications of cubic functions. You are making an open-top rectangular box from an 8 by 15-inch piece of cardboard. By cutting square pieces off of each corner and folding up the sides. We're going to find the dimensions of such a box with the largest volume. Each square that we cut off would have the sides equal to x. Do we have a limited domain for the x values? Yes, we would. Our smallest side, yes, we would. Why? Okay, keep in mind that our smallest side is 8, and half of that is 4. So that's very important. Okay, so each square that we cut off would have the sides equal to x. Suppose that x measures larger than 4 as shown to the right. It wouldn't make sense for two squares to add up to 8 or more inches. After all, each side is only 8 inches. Remember that volume is equal to length times width times height. Now we need a volume formula in terms of x. Here's our length, 15 minus 2x. Notice how you have two x's on each corner, and that's what you have to subtract. Look at our width. It's 8 minus 2x. And then our h, our height, is just x. So the formula V is equal to 15 minus 2x times 8 minus 2x times x. And when you FOIL it out, that is the cubic function you would get. To maximize the volume, we can find any critical points and use them to find the maximum. So in calculus, you're able to do this by taking the derivative. And then you factor what you have left. And notice that we have two x values, 5/3 and 6. But remember that we told you that the domain was between 0 and 4. So 6 is greater than 4. So we're not going to be able to use that. So the only one that we have left is 5/3. However, we will not be using the calculus. Instead, we're going to use Desmos. So you're going to copy this equation into Desmos. V equals 15 minus 2x, 8 minus 2x, and x. This is a cubic equation because we have three x's. We will look for the maximum height of the graph. So here's our equation typed into Desmos. Notice that on the x-axis, the two black dots. They are between the x-intercepts of 0 and 4. And this always gives you the domain. The domain is between 0 and 4. Notice the coordinates of the first maximum. It's 1.6667 and 90.741, which means it's 5/3 and 90.74. The height 5/3 is the x value of the ordered pair. The y value gives you the maximum volume of the box. So the maximum volume of the box when the height is 5/3 is 90.741. Notice that we do not use the whole graph, just the first maximum. Okay, so our dimensions are, when we plug in the 5/3 for our x's, our length is 35/3. Our width is 14/3. And remember, the height is 5/3. And the maximized volume is 90.74 inches cubed. How to analyze maximum box problems. Here's another problem. An open box is to be made from a 10-inch by 12-inch piece of cardboard by cutting x-inch squares from each corner and folding up the sides. So what are your numbers? The width is 10 and the length is 12. What's the x? Remember that the x is the height, and we don't have that measurement. So we're going to write a function giving the volume of the box in terms of x. Remember, your volume is length times width times height. And remember from the picture of the box that you have two x's per side that you're going to subtract from the length and the width. So we have 12 minus 2x and 10 minus 2x, and then times the height of x. What are the dimensions that maximize the volume of the box? We're going to plug that formula into Desmos, and we find that we have 1.81 for our x value and 96.77 for our y value for the maximum of the first maximum. All right, we can also find out what the length and the width and the height really is for this box. The height is given from your ordered pair, 1.81. The length would be your 12 minus 2 times 1.81, which is 8.38. And the width is 10 minus 2 times 1.81 equals 6.38. And so now you've answered all the questions from the problem. The end, and thank you for participating.